Hi students, welcome to the video lecture on the subject Basic Thermodynamics. So today we are going to start with the first module, that is Fundamental Concepts and Definitions by Professor Prashant S. Shedbalkar. So in the today's class we are going to cover introduction to the thermodynamics. What do you mean by thermodynamics? And what are the different types of thermodynamics? That is classical and statistical thermodynamics. We are going to study the application areas of thermodynamics. Last one is what is a system and what are the different types of the system. First, introduction. This thermodynamics. The name thermodynamics, it stems from the Greek word, that is therm means heat and dynamis means power. The conversion of heat into power takes place, whereas the conversion of power into heat takes place. So this thermodynamics, it is the study of the effects of work, heat and energy on the system. This thermodynamics, it is the branch of science which deals with the study of various forms of energy and their interconversions. It explains the interaction between heat, work, and other physical properties such as pressure, volume, and temperature of the working substance. See, the observations and the common experiences, it has been formulated into the laws of thermodynamics. So here we are going to study mainly three laws. First law of thermodynamics, second law of thermodynamics, and zeroth law of thermodynamics. These laws and the concepts of thermodynamics are important in the innovative design, development, and the improvement of the various engineering processes and equipment, especially in the field of energy utilization. So now we will study, there are two types of thermodynamic systems. That is, in the two ways we are going to study this thermodynamics. One is classical thermodynamics and another one is statistical thermodynamics. So we already know that the substance, it consists of a large number of particles called molecules, and these properties of the substance naturally depend on the behavior of these particles. For example, if I want to give you the pressure of the gas in the container, it is the result of the momentum transfer between the molecules and the walls of the container. However, one does not need to know the behavior of the gas particles to determine the pressure in the container. So it would be sufficient if we attach a pressure gas to the container. Then we are going to read how much the pressure of the gas is in the container. So this macroscopic approach to the study of thermodynamics, which does not require a knowledge of the behavior of the individual particles, it is called as the classical thermodynamics. The study of thermodynamics which does not require the knowledge of the behavior of the individual particles is called classical thermodynamics. See here, so this is the gas. If I want to measure the pressure of the gas in the container, here we are not going to study the behavior of the gas particles, each and every individual behavior of the gas particles to determine the pressure of the gas. If we attach just the pressure gauge to this container, we are going to measure the pressure of the gas which is present in the container. So in statistical thermodynamics, it is the study which is based on the average behavior of the large groups of individual particles. It is called as the statistical thermodynamics. If we want to measure the pressure of the gas in the container, we are going to study the average behavior of the large groups of the individual particles. That type of study, it is called as the statistical thermodynamics. So usually this classical thermodynamics is usually studied. So this classical thermodynamics is also known as the macroscopic approach. Macroscopic approach is also known as classical thermodynamics, whereas microscopic approach, it is known as statistical thermodynamics. So now let us study some difference between this. See here, the analysis of the macroscopic system, it requires a simple mathematics formula to determine the pressure. But in a microscopic approach, the value of the quantity changes with time. So advanced statistical and mathematical methods are needed to explain the change in the system, because here we are going to study the individual behavior or the average behavior of the large groups of the individual particles here. So it is very complicated. Here in this macroscopic approach, a very few properties are required to describe a system. But in the microscopic, a very large number of variables are required to describe a system. And this macroscopic approach, it is very quite simple, but this approach is complicated. So now we'll study where these application areas of thermodynamics. You can see everywhere this thermodynamics is required, because in our day-to-day life also we are coming across the conversion of energies, that is heat into power or power into heat. Every day we are coming across these energy utilizations. You can see in the human body also the thermodynamics is applied in the air conditioning systems, where the energy and the heat and power energy conversions are taking place. Even in the power plants, you can see in the car radiators also. So cold water is entering in, hot water is coming out, there again energy conversion takes place. Power plants, where we are going to generate the steam here, we are going to utilize that heat energy to convert power. Refrigeration systems, where the heat energy, it is entering from the low temperature system to the high temperature system. So the applications of thermodynamic laws and these principles are applied in almost all the fields of the engineering technology, especially in these steam and nuclear power plants, also in the IC engines, in the gas turbines, in the chemical process plants, air compressors, air conditioning systems, car radiators, etc. So it is having a very wide application range of this thermodynamics. So now we will study what do you mean by this thermodynamic system and surroundings. System, it is defined as a quantity of matter or a region in space which is selected or chosen for the study purpose. Any region in space which is selected for our study purpose, it is called as the system. So this is my system. So I can take anything, any region in space which I am choosing for my study purpose, it is called as the system. I may consider the pen as my system. I may consider um, the gas which is contained in the container. I may consider gas as the system because I am choosing that area, the gas, for my study purpose. I may consider any fluid is my system. That much region, I may consider book as my system. So any region in space which is chosen or selected for the study purpose, it is called as the system. And the mass or a region, the mass or a region outside the system, it is called as the surroundings. The real or the imaginary surface. So this is the real surface, the real or imaginary surface that separates both the system and the surroundings. It is called as the boundary. So this is the real surface here. So some imaginary surface may be there which is separating both the system and the surroundings. So now coming to this point, the boundary. The boundary of the system, it can be fixed or movable. And this boundary, it is the contact surface which is shared by both the system and the surroundings. So mathematically speaking, this boundary has zero thickness and thus it contains neither any mass nor it occupies any volume in space. So next we will see how the boundary is fixed, where the boundary is movable. We'll see in the next. So this is about the system, surroundings and the boundary. So again, the systems are classified into mainly three types. One is closed system, second one is open system, and third one is the isolated system. So closed system, it consists of a fixed amount of mass and no mass can cross the boundary of the system. That is, no mass can enter the system and no mass can leave the system. But energy, in the form of heat or work can cross the boundary of the system. And the volume of this, the closed system, it does not have to be fixed. Mass will be constant, but the volume of this closed system, it does not have to be fixed. And this closed system, it is also known as the control mass. This closed system, it is also known as the control mass. So you can see here, we have taken here gas of volume. The volume of this gas is 1 meter cube, whereas the mass of the gas is 2 kg. So this is the piston and this is the cylinder arrangement in which gas is present here. So this is our boundary here, piston. So this is also our boundary here. So gas becomes our system and everything external to the system is the surroundings here. So when we start heating this gas which is in the cylinder, the gas starts to expand and it pushes the piston upwards. That means here the boundary is not fixed. Here the boundary is movable. You can see here the mass will be same only. The mass of the gas, it will be 2 kg only. When the gas is heated, it is going to expand the volume of the closed system. It may not, does not have to be fixed. It may be fixed or it may not be fixed. Here, see here, the volume of the gas becomes 3 metric cube. Volume has increased here, so pushing the piston upwards. That means the boundary is movable here. Already we have explained the boundary may be fixed or it may be movable. So the best example, if we can give you, the for closure system, the pressure cooker, or the gas which is confined, which is contained between the piston and the cylinder arrangement. So this is about the closed system. Next we will study open system. So in the open system, it is also known as control volume. Here both mass and energy in the form of heat or work, it can cross the boundary of the system. Here both mass and energy can cross the boundary of the system. So we can take the example of the a cup of hot coffee. So here mass is crossing the boundary of the system. So here boundary means the top surface of the cup, it becomes the imaginary boundary, and the cup which is present, it becomes the boundary, physical boundary, and the outside upper portion, it becomes the imaginary boundary. You can see here both mass is also transferring and the energy in the form of heat, it is also transferring the boundary of the system. You can see water heaters, car radiators, the turbines, compressors. So these are all the examples of the open system. And another main thing in this open system, the boundary of this open system, it is known as the control surface. The boundary of this open system, it is known as the control surface. You can see here. So if I will assume this is the nozzle example, so this is the real boundary, physically it is present here. See here, some fluid or some mass is entering here in and some mass is going out here. So here no any physical boundary is present, so we will consider this as the imaginary boundary. Here this is the imaginary boundary, we can consider this is the imaginary boundary here, because no any physical surface is present here. You can see here I have given the examples of this closed and the open system. So here no mass is crossing the boundary of the system, the gas will be present here, the only energy in the form of heat or work will cross the boundary of the system, so this mass will be constant here. This is the example of the gas in the piston cylinder assembly. You can see here it is for control volume, it is also called as the open system. Here both mass and energy exchange takes place. Here fuel is entering here in, some work is the combustion of the fuel takes place, it performs some work in the automobile engine and the exhaust gas out, that is mass is entering, mass is going out also. Here air in and uh, both air and the fuel in, so combination of the exhaust gases after combustion, so the exhaust gas out. So this is the boundary of this open system, it is called as the control surface. You can see here is the boundary of the open system, it is called as the control surface. See here dotted lines, it is nothing but your control surface here. Last one we will study isolated system. In this isolated system, both mass and energy will not cross the boundary of the system. Here mass is also constant, energy is also constant. We can consider the whole universe as an isolated system, because here no mass and no energy is crossing the boundary of the system. And another simple example if we can take, it is the flask. Thermos flask is the example for an isolated system where both mass and energy are not crossing the boundary of the system.